Welcome to our lecture on the vibrating membrane model. Today, we are going to explore the fascinating mathematics behind how surfaces like musical drum heads and trampolines move when they are struck. We will build our understanding from the ground up, translating physical movement into a beautiful partial differential equation. Let us dive right in and get started. Now that we know our topic, let us define what we mean by an ideal vibrating membrane. Why does this matter? Because real-world materials are messy, and to understand the core physics, we must strip away the complexities. We imagine a perfectly flexible, infinitely thin two-dimensional surface. It offers absolutely no resistance to bending, only to stretching. We assume it is pulled tight with a constant, uniform tension across its entire area. Finally, we assume the vibrations are very small compared to the size of the membrane, moving only slightly up and down. Before we see where it comes from, let us look at the mathematical model that describes this movement. This is the famous two-dimensional wave equation. Conceptually, it tells us that the vertical acceleration of any point on the membrane is directly proportional to how sharply the membrane is curved at that exact point. Let us break down the symbols. The function u represents the vertical displacement. The constant c squared represents the ratio of tension to mass density, which determines the wave speed. The upside-down triangle squared is the Laplacian operator, representing the total spatial curvature in both the x and y directions. If the tension increases, the wave speed increases. Before we move on to the proof, let us see this formula in action with a concrete example. We are given a rectangular drum head stretched with a uniform tension of 400 newtons per meter. The surface mass density is 0.01 kilograms per square meter. We are asked to calculate the speed of the waves and write the specific partial differential equation for this drumhead. We choose our wave speed formula because it directly relates our given tension and density to the speed c. We substitute 400 for tension and 0.01 for density. Continuing with our calculation, we simplify the fraction. Dividing 400 by 0.01 is mathematically identical to multiplying 400 by 100, which gives us 40,000. Taking the square root of 40,000 gives us a final wave speed of 200 meters per second. Physically, this means any ripple will travel across the drumhead at 200 meters every second. Finally, we plug our c squared value, which is 40,000, back into the general wave equation. This final answer perfectly models the specific vibration of this exact drumhead. Now that we have used this formula, let us understand where it comes from by deriving it. We are setting out to apply Newton's second law of motion to a microscopic rectangular patch of the membrane. Newton's law states that force equals mass times acceleration. First, we define the mass of our tiny patch. It is simply the surface mass density ρ multiplied by the tiny area, delta x times delta y. Next, we need the vertical acceleration. In calculus, acceleration is the second partial derivative of the vertical position u with respect to time t. This sets up the right side of our equation. Continuing our derivation, we must now find the net vertical force acting on this tiny patch. The only force acting on the membrane is the tension pulling on its edges. Because the membrane is slightly curved as it vibrates, the tension forces on opposite edges do not perfectly cancel each other out. Instead, they leave a very small net vertical component. The mathematical reasoning here is that the difference in the slope of the membrane from one side of the patch to the other creates this residual upward or downward force. Let us visualize this curvature and tension in the next slide to make it clear. Here we are looking at a highly magnified view of a tiny membrane element. Notice the axes. X and Y form the horizontal plane, while U represents the vertical displacement. The arrows labeled T represent the uniform tension pulling on the edges of the patch. Because the surface is curved, you can see that the tension arrows are slightly tilted. This tilt means they have a vertical component. The diagram beautifully illustrates how spatial curvature directly results in a net vertical force, which is the core physical mechanism driving the vibration. Now that we have visualized the forces, let us write them out mathematically. The net vertical force from the x direction depends on the tension, the length of the edge delta y, and the difference in the partial derivatives of u with respect to x. This difference in first derivatives represents the change in slope. We write a similar expression for the net vertical force from the y direction. By adding these two forces together, we get the total net vertical force. We then set this total force equal to our mass times acceleration expression from earlier. This connects the spatial curvature to the temporal acceleration. We have reached the final stage of our derivation. To simplify our massive equation, we divide every term by the area of the patch, delta x times delta y. Now we apply a fundamental concept from calculus. We take the limit as our tiny patch shrinks down to a single point, meaning delta x and delta y approach zero. As we do this, the complex difference quotients perfectly transform into second partial derivatives with respect to space. Finally, we divide by the density ρ and define our wave speed squared. This gives us the final result, the beautiful two-dimensional wave equation. So we have proven that the wave equation holds. This brings us to the next major question. How do we actually solve it? The equation is a complex partial differential equation, which is notoriously difficult to solve directly. This is why the method of separation of variables matters so much. It is a powerful mathematical technique that allows us to break this massive, complicated equation into three simpler, highly solvable ordinary differential equations. By assuming the solution can be split into independent parts, we transform an impossible problem into a manageable one. Let us look at the mathematical assumption that makes this possible. We assume that the vertical displacement function u can be written as the product of three separate independent functions. Conceptually, this means the shape of the vibration in space does not change its fundamental form over time. It only scales up and down. The function capital X depends exclusively on the horizontal position x. The function capital Y depends exclusively on the depth position y. And the function capital T depends exclusively on time t. If any of these variables change, they only affect their specific function. Now we will apply this assumption to our wave equation. We are setting out to find the second derivatives of our assumed product solution. When we take the second partial derivative with respect to time t, the spatial functions capital X and capital Y act as pure constants, so we only differentiate capital T twice. The mathematical reasoning is identical for the spatial derivatives. When differentiating with respect to x, the functions y and t are treated as constants. This step is crucial because it prepares our separated functions to be plugged directly back into the original wave equation we derived earlier. Continuing our separation process, we substitute our new second derivatives back into the two-dimensional wave equation. To truly separate the variables, we divide the entire equation by the product of x, y, and t, and also by c squared. The mathematical reasoning here is brilliant. We end up with an equation where the left side depends entirely on time and the right side depends entirely on space. The only way a function of time can always equal a function of space is if both sides equal the exact same constant. This gives us our final result, our first separated ordinary differential equation. Now that we have seen the mathematics, let us understand why this model is so important in the real world. The vibrating membrane model extends far beyond musical instruments like drums or tambourines. It is the fundamental mathematical foundation for designing acoustic sensors and microphones, where a tiny membrane converts sound waves into electrical signals. In biology, it helps us understand how the human eardrum captures sound. In structural engineering, similar equations model how thin metal roofs or bridge decks might vibrate dangerously during high winds, allowing engineers to predict and prevent catastrophic resonance. We have covered a lot of ground today. Let us review our key takeaways. First, the vibrating membrane model uses Newton's second law to relate the vertical acceleration of a surface to its spatial curvature. Second, this relationship is mathematically expressed as the two-dimensional wave equation. Finally, we can solve this complex equation using the method of separation of variables, breaking it down into simpler ordinary differential equations. You now understand the core physics of vibrating surfaces.